So the purpose of the next section is to talk about maximum and minimum values of the function. We're going to be using these concepts in application problems later on in the chapter. A lot of these problems will be helpful when we're trying to do optimization, which are very common application type problems of maxes and mins. And what we did in the last chapter with the derivatives is going to be really helpful to us now, because if we have a baseline of how to take a derivative, kind of what those values mean, that's going to be useful when talking about maximum and minimums. So let's just kind of review what a maximum is, what a minimum is, and we'll kind of fill in some definitions and then look at some diagrams. So a function has an absolute maximum at c. So let's just say that this c is like an x equals c. So it's some x value. If f of c is greater than all of f of x for all x in the domain. So that basically says that this f of c is talking about a y value at the x value of c. And we're saying that an absolute maximum happens if this y value is greater than any y values in the function. On the other side, what if we wanted to say a function has an absolute minimum? Well, the opposite would basically happen. Then the y value at x is equal to c would be less than any of the other y values in the function. And we can say that these maximum and minimum values are called the extreme values. Sometimes you'll see them as extrema. So if you see that those are kind of interchangeable. And some of these are going to be pretty intuitive. Hopefully you kind of have an idea of what a maximum and a minimum looks like, but we're just going to kind of add some other things in here. So we can say that an absolute minimum basically happens at the lowest point in the graph. So over here, at this point, this would be the lowest point of any other point in the graph. So we can call this point over here the absolute minimum. And then the absolute max would happen at the highest point. So up here, this would be the highest point in the graph because there's no other points that are higher than that one. So we can call this one the absolute maximum. But these other kind of peaks and valleys of this graph also have names. We can call these local maximums and local minimums. And local maximums and minimums happen within the graph. So a local maximum and a local minimum would never actually occur at an endpoint. So I can call this kind of high point of this part of the curve a local maximum. I can also, even though this is an absolute maximum, you can have absolutes and locals at the same point. So I can also call this point a local maximum. And even though this kind of looks like a high point here, again, the locals don't happen at endpoints. So we actually don't want to call this any local. If this was like an absolute, then we can use it at an endpoint, kind of like what we said the absolute was over here. But again, since it doesn't have anything to compare to on the other side, we actually don't know the behavior of the function, whether it stops or whether it continues here. So we don't want to make an assumption about whether this could be a local max or min. So we kind of identify what the local maxes are. This point right here and this point right here would be considered local minimums because they're kind of in kind of a low point of the graph in relation to the points around it. So this is a local min, and this is also a local min. Okay, and again, we don't want to call this a local minimum over here because it's an endpoint. We don't have anything to compare it to over here, so we don't know what the behavior of the graph is doing after this point. So just to kind of put a formal definition here, a function has a local maximum at c if f of c is greater than f of x, but just for all x in the open interval near c. So you're only looking at kind of the places around that point. Same thing with the local minimum. If f of c is less than or equal to f of x for all x in the open interval near c. again, you're just comparing it to the points around C. Okay, so I'm just going to write a little note, and this is just kind of illustrating what that's talking about. So I'm just going to put a little star here, and I'm going to say, in order to be a local max or min, there need to be values on both sides to compare. Which is kind of what I was talking about up here. We said that an absolute minimum can happen at an endpoint, but a local can't happen at an endpoint because you need something to compare to. And I'll just put this as a note. An absolute max or min can occur at an endpoint. All right, so let's just take a look at a couple of examples of identifying local maxes and mins and absolute maxes and mins, and then we'll talk about how these are useful to kind of what we've been doing in calculus so far. So I'm just going to talk about a couple graphs here. So first thing that I want to identify of this graph is its domain. So it looks like our domain is going from the x value of 0 to the x value of 3 pi over 2. And within this domain, the absolute maximum value would be this point over here. And the way that we write it, usually people would say, okay, the absolute max would be the point 0, 1. We actually write this in notation indicating that f of the x value of 0 is equal to 1. So this point of 0, 1 would kind of correspond to this notation of f of 0 is equal to 1. Our absolute minimum value, so the lowest point in the graph here would be this point pi negative 1. But if I want to write it in notation, that would be f of pi is equal to negative 1. And then I want to identify a local maximum value. Well, I have an absolute maximum over here, and that's really the only high point that I have on my curve that's higher than all the other points. And remember that we don't want to name an endpoint a local maximum. So in this case, we actually don't have a local maximum. There's nothing within the domain here that has something to compare to on the other side. That would indicate we have kind of another high point. We don't have a local minimum though. This absolute minimum can also be the same thing as a local minimum. So a local minimum we can call f of pi is also equal to negative 1. All right. So our second graph, we're looking at kind of this. It looks like something that's approaching an asymptote. So it looks like our domain is from negative 1, not including, because that's where our asymptote is. And then we're going to positive 4. Here we are looking for an absolute maximum value, but if we think about what's happening, this curve is actually going to increase without bound forever. So there actually is no absolute maximum value. Absolute minimum value, though, we do have the very low point of the graph over here would be at the point 4,1. So f of 4 is equal to 1. Since we don't have an absolute maximum, since again, this graph is increasing without bound, we actually don't have a local maximum either. And we actually do not have a local minimum value here either. We know that this is the absolute minimum, but again, we don't want to put a local on an endpoint. So let's talk about this last graph. So it looks like our domain here is all real numbers, negative infinity to positive infinity. Our absolute maximum value, again, kind of similar to the last graph, if these endpoints are increasing forever, we are not going to have a absolute high point. We do have an absolute minimum point down here. This is definitely the lowest point on the graph. So I would say that's about probably negative 3, negative 3. So f of negative 3 is equal to negative 3. We do have a local maximum value. So if we kind of look here, this is a high point on our graph. We have points on the other sides to compare to. So it looks like I'd say the local max would be about, I don't know, f of 0 is equal to about, I don't know, 1 1/4, 1.25. And then local minimums, we have this point over here as well as this point over here, again, because we can mark the absolute minimum as a local minimum as long as it has something to compare to on either side. So I'm going to say f of negative 3 is equal to negative 3. as well as I'm going to have to do a little bit of estimation here. I don't know, maybe 2 1/4 would be the x value there. And then, I don't know, -3/4, let's just say that. So f of 2.25 is equal to -0.075. All right, so what if we wanted to sketch something? So example A down here, we're given some information. We want to sketch a graph that would fit these kind of restrictions. So there's a lot of things that you can do here for these types of problems. Here we're told that we have a domain of 0 to 8. We want an absolute maximum at the x value of 0. So I don't know, I'll just put a high point up here. That's my absolute max. Absolute minimum at 3. So I don't know, I'll just put a point down here. And we want a local minimum at 7. So I don't know, I'll put a point down here. We know that this is the absolute minimum, so it's got to go farther down over here than over here. So I don't know, it might look something like, oh, there's a lot of, so stop at 8 right here. So we'll put an endpoint here, cross off the rest of the graph. So I don't know, it might look something like that. Again, there's a lot of stuff that you can do here with this. You could make your graph kind of go a little bit steeper and go above the x-axis as long as you're fulfilling these restrictions. All right, let's look at the other one. Local minimum at 4 is continuous but not differentiable at 4. So local minimum at 4. Just make myself a little 1, 2, 3, 4, 5, 6. So if we know that we have a local minimum at 4 and we know it's continuous but not differentiable at 4, remember that when something is continuous but not differentiable, there might be some sort of like a corner or a cusp. So you can include something like that in your graph. You can't have any breaks though because it does need to be continuous. So my graph might look something like that. So definitely a local minimum. It's kind of a lower point is compared to all the points around it, and it is continuous but not differentiable because I have a little corner there at 4. All right, so let's get into some calculus stuff. So now that we've seen how some functions have extreme values, we're going to look at some graphs that have some local extrema. So if you notice here in our first graph, our local extrema happen at these points here. And at these points, we have horizontal tangent lines. So at these points, our tangent lines are horizontal, which means that our slope or our f prime is equal to 0. I'm going to say at the local extrema. And if we look at our kind of local point over here, we also have some local points up here. But again, that kind of fits with the same thing that I just talked about. Our tangent lines would be horizontal. We know that at this point with the corner or the cusp, it is continuous, but we are actually not able to say anything about the derivative at this point because it doesn't exist because of that corner or cusp. So we can say that f prime is undefined at that point, again, due to the corner. So we can say that the local minimum occurs at a point where the function is not differentiable. And these two concepts are pretty important for what we're going to be talking about because these are really important things when we're talking about something called critical points. So when the tangent line is horizontal or when the function is not differentiable, there's going to be something that happens at these kind of two instances called a critical point. And what is a critical point? Well, a critical point is a number. We'll call that number C in the domain of F. And we can say it is a critical point if either 1, f prime of c is equal to 0, so our tangent lines are horizontal, or 2, our f prime of c doesn't exist, which has to do with like the corner or the cusp idea here. Okay, so how do we know whether something's a critical point without looking at the graph? Like, how do I know whether a tangent line is horizontal, or how do I know whether something is undefined at the derivative? Well, this is where our calculus is going to come in. So if we are given a function without looking at its graph, we want to know what its critical points are. So what we can do is we can take this function, find its derivative, and then find the critical points using either 1 or 2 up here. So if I take my derivative here, my f prime is going to be equal to 3x squared minus 18x plus 24. What I basically want to do with this f prime is I want to find the places where the tangent line is going to be horizontal. So this derivative I'm going to take and I'm going to set equal to 0 to figure out where those places are that the tangent line is horizontal. So take that, set it equal to 0. Do some algebra here. Here, this one looks like I can factor out a GCF of 3. So then I will get, if I use my zero product property here, an x value of 4 or an x value of 2. So these we can call critical numbers. But what we want to do is we want to find the critical points. So at these x values, what is the point where my tangent line is horizontal? Well, to figure out what the point is, I have an x value of 2. I want to figure out what the y value is. I have an x value of 4. I want to figure out what the y value is. I can go ahead and take these numbers and plug them back into my original f of x function. So I'm going to do f of 2. So 2 cubed minus 9 times 2 squared is 4, plus 24 times 2 minus 10, I believe would give me a 10. And then I can do the same thing for the 4. So f of 4, 4 cubed minus 9 times 4 squared is 16, plus 24 times 4 minus 10, I believe would give me a 6. So my critical points would end up being 2, 10, and 4, 6. So this is telling me at this point and at this point, the tangent line would be horizontal. Okay, so let's find the critical numbers of this function. So f of x is equal to x minus 2 sine x. So pretty much the same idea. We want to go ahead and take the derivative of this, which would be 1 minus 2, derivative sign would be cosine. So set this equal to 0. So 1 minus 2 cosine of x, which would give me 2 cosine of x is equal to 1. So cosine of x would be equal to 1/2. Take my inverse cosine. And then that's going to give me 2 x values. So my cosine is positive 1/2 at pi over 3 or 5 pi over 3. And these would be my numbers. Again, if it's just asking for numbers, this is really just asking for what the x values are. But that would only be in one revolution of the unit circle. So here, we're not given that we're only going around the unit circle once. We want to capture all possibilities. So our critical numbers would be pi over 3 plus 2 pi n, and then 5 pi over 3 plus 2 pi n. So to capture all possible values, no matter how many times you go around the unit circle, these would be our critical numbers.